Programming Throwdown, Episode 82, Reactive Programming and the Actor Model with Jonas Bonaire. Take it away, Jason.
Hey everyone, so we have a really cool interview. I'm sure a lot of you know about Scala and Akka. You've heard about this. We've talked about this on the show. And we have Jonas Bonaire, who is, are you the original creator of Akka? Is that right?
Yeah. I started it back in 2009. Or actually, the first launch of the product was in 2009. I started hacking on it a year earlier. So, yes.
Cool, excellent. And Jonas is going to explain kind of reactive programming, the actor model. He's going to talk us through sort of that whole kind of revolution. I think it's amazing to do, especially for UI and for a lot of other kind of processes, to have this sort of model. And Jonas is going to really, he's an expert. He's going to explain it to all of us. So Jonas, why don't you kind of tell us your background, why you got, how you kind of ended up getting really into this sort of programming model. Is it sort of a series of anti-patterns that you saw along the way that made you say, oh, we need to build something new here? So what was the motivation for that? And what's that journey kind of been like? It's been, I guess, about 10 years, right?
Yeah, time flies by quickly. Yeah, it's actually started a bit earlier than that even. It's so my journey into distributed systems and concurrent system and stuff like that actually started the journey towards Akka and the actor model there, and everything started back in I joined BA Systems back in the day, and I was working then on an open source project called AspectWorks. Aspect-oriented programming were quite popular back then. I don't know if AspectJ and stuff. AspectWorks was later merged with AspectJ and etc. Right, so there was a lot like bytecode weaving and having this sort of dynamic capabilities to Java and any language that implemented AOP. But so I actually worked on that open source project while working at BA Systems. But then I was headhunted by a small startup in 2003 or something like that used the technology that we had built, which was of course open source. A small startup in the valley called Terracotta, and they did distributed systems and essentially tried to sort of cluster the JVM underneath the JVM itself to make and maintain the programming model of sort of threads and locks and sort of stretch that out across a set of distributed nodes and try to do sort of all the messiness underneath to make that work. Essentially, if we should get geeky here, so the way it actually worked was that the sort of locks and sort of memory barriers were sort of translated into sort of transactional scope. So it was those transactions that were sort of maintained across the JVM, and they did that, completely transparently using aspect-oriented programming.
So in that case, how do you
and the tech that I had built?
Yeah, how do you handle the data dependency there, right? I mean, if somebody's treating it as like threads, they might not be aware of that they have to broadcast all this data, right?
Exactly. I mean, it's when I joined the company and actually when promoting it and stuff, we actually went quite far, selling people on the model. But the thing is that it was a completely broken model from the start, and that started to grow on me after being out at clients. We after a couple of years. We never really got it to work. No surprise. I'm now a firm believer of this sort of opposite way of approaching distributed systems, where you sort of embrace the network, you embrace the constraints of the network, and instead of trying to hide it, it turns. If you try to hide it, in my opinion, it turns into this leaky abstraction that leaks so much that it becomes more or less useless. We've seen this many times in the past with RPC and distributed objects or XA or anything like that. It's actually it works to the point where it doesn't work, and when it doesn't work, everything falls apart.
Right.
Where you have network disconnects, partial failures, you have really no idea how you can recover from. etc. So that's made me completely lose faith in that model, and actually in general, the way I was sort of doing after that, I was doing consultancy on distributed system in Java in general. Embrace Corba and all the tools that they have, EGBs and all the tools that they have there. And it started to grow on me that all of this is just the wrong way of approaching the problem. And I went through this crisis in a way, and I started to sort of dig through a lot of research papers and stuff. And then it started. Then I chatted with a friend that had been actually all the way since school been programming in Erlang. He went straight to Ericsson, and Ericsson developed this language, this very esoteric and quite obscure language called Erlang. And I just when talking with him, I sort of realized that wow, this is the model I've been looking for. I mean, communication or distributed communication is first class. Where we have true isolation, failure can't cascade across components or across nodes, as we even seen, often in Java and things like that. And that sort of set me on the path. First, learning Erlang for real. So I've been tinkering with it back in school, and I of course knew what it was, being Swede and having friends using it, but I never really sort of took it seriously. But I felt like, of course, I can't program Erlang day in and day out. All my clients, my whole life is served on the JVM. Then I better find a way to port that model, because essentially the model, the principles, they're so good, over to Java, and that's how I started Akka. Back in 2008 was that. So.
Oh, I see. So, are there any sort of did you encounter any sort of really fundamental limitations of or say differences between the JVM and Erlang that were like serious roadblocks for Akka, or was it more of like just a mechanical day in day out, let's get it done? Like, were there any like real technical hurdles there?
Yeah, one of the things that people always tend to point out when they come from Erlang, and they're absolutely right about that, is that you can't have such a thing as true isolation on the JVM, because it is a shared heap, so sort of isolation is only by convention, but by sort of trying to have a programming model that sets up the boundaries and tries to make it easy to do the right thing. And regardless, even if you use Akka, you can always use reflection and stuff like that to bypass that. And if you really, really want to shoot yourself, so that's one of the things that's hard. And also, things like garbage collection. Erlang has garbage collection, but it has it like per actor. So it's not that. So you have more fairness, because you have control over the garbage collector. While since Akka runs on the JVM, there's really no control we have over such low level things, and sometimes it can be more of sort of long latency pauses and stuff like that. But of course, very often those can be mitigated by doing the right thing, and we try to sort of push people in the direction of doing the right thing. Not creating too much garbage and stuff like that.
That makes sense.
But still, it's not the same. It's not the same thing as an Erlang, where they have full control over everything. The VM is built with actors in mind, which is not the case for the JVM.
So in the case of Akka, I mean, you could have all the actors running in separate processes, right? Then they right. would, but that probably has its own expense, right?
Yeah, no, we don't do that. We sort of. So the way it works, if we should go into how into the actor, should we first explain the actor model?
Yeah, that's a good point. So maybe let's spiral back a little bit and talk about what is the actor model, what is reactive programming, kind of how is that, if someone comes, let's say they're in first year of university. They've taken system software and they've written some code in C, and they say, what is the actor model? What does this mean?
Yeah, Sure. The actor model is actually quite old. I learned it from Erlang, but Erlang took it from papers by Carl Hewitt. And that he wrote I think back in the early 70s or something like that.
Mm-hmm.
I don't remember the exact date when the first came out. Very early in the 70s. And the actor model it's a complete computation model. I mean, Turing complete, like Lambda calculus is a sort of foundational computational model. That has a sort of little bit different take than most of the other ones. It models communication as sort of first class and communication and behavior, and it's called the actor model because actor is the unit of computation. It's sort of the unit of work or that you have, actors are extremely lightweight. At least in sense. Now we're getting down to how they usually are implemented. But both in Erlang and most C C++ implementations that I've seen, especially as well as Akka, implement actors in the way that they are extremely lightweight in terms of how they use resources. For example, Akka you can run millions of them on a regular laptop, and they don't consume the reason why.
Oh, I see. So it's almost like a green thread, like a green thread or a coroutine or something like that.
Exactly. So we do multiplexing on threads, so you have like this n:(m) mapping of actors to threads, and in Akka it's called the dispatcher, but it's the sort of thread pool that you scheduler that you run them on.
Yeah, for people
in Akka it only consumes like heap.
Yeah, just for people who might not be familiar. So basically, you have, if you create a thread, or even to a greater extent, you create a process, this is actually, a lot is happening under the hood. You might say just new thread, and it seems really quick, or STD thread or something in C++. But actually under the hood, the OS is doing a ton of work there. And so you can't realistically create, let's say, 1 million processes, on one computer. It's just not practical. And so a lot of these... you see these green threads or these coroutines. The idea is the system creates, let's say 32 threads right at the beginning. And then when you say, hey, I want to do this bit of work on the side, it just uses one of those 32 threads. It's already been created. And if you try and do 33 things at the same time, that 33rd thing just kind of sits in a queue. And once one of the threads is free, it starts, offloading that queue.
Right. Exactly. So that's essentially how we implement actors in Akka. I mean, nothing prevents you from implementing the actors as having one actor per process, but sort of I think the whole benefit of actors sort of falls apart, in my opinion. The actors are so great because they are not mapped to threads, that you can easily create, thousands or millions of them and sort of spread them out on the cluster. The way I tend to look at them is like very similar to how things work in nature. Like mapping them to how like ant colonies work. Like where you, or bacteria or something like that, where you have like you have so many, right? So if a few of them fails, it doesn't really matter because others can take over. Where the failed ones started, and without sort of really affecting the overall health of the application, and that's essentially how I like to look at actors, and why I see them a really powerful model for the cloud. Where you have all these compute resources and all these nodes available. But a few other things that sort of are characteristically important to actors is that that all communication is sort of first class. It's sort of built into the model, and communication is sort of distributed by nature or by default, where local communication is just an optimization. So it is sort of a unification of distributed and local communication. It means that they both look the same. It looks the same if you communicate with an actor that sits right next to you, or lives in another node or in another data center. It looks the same, and this is what we mean, what we call location transparency. And one of the benefits of that is that if you have a reasonably advanced runtime underneath here that sort of understands how actors are being used and which ones are overloaded, which ones are underutilized, which ones are actually failing now and stuff. that runtime can optimize these things by moving the actors around. And sort of this is sort of, in my opinion, the key to location transparency, that the cluster can sort of optimize itself by shuffling actors around on different nodes without the experience from the user perspective, the client. He never really has to even know that is going on, and that's a lot thanks to the dynamicity of the actor model, that the actors can sort of. One thing that I didn't say is that the way you communicate with an actor is usually through some sort of reference. In Erlang, you have what is called the PID, the process ID that you send messages to or communicate with. In Akka, we have what is called the actor ref. So you never communicate with the actor directly, but only through this sort of proxy or this reference. So this means that the actor can live anywhere. And this sort of level of indirection also gives a runtime the opportunity to manage failure in a transparent way by sort of failing over to other actors, even on other nodes, or to route messages, to other actors of the same type and things like that. So that's a very powerful thing, and this is also leveraged in the failure model. So that is sort of one of the key things also that I see from the actor model, that it has this notion of supervision, that actors watch out for each other. It's completely masterless, decentralized. There's no special nodes, no special actors or anything like that. But each actor can watch out for other actors. And if his buddy sort of dies, he will get a notification and say, "Oh, your buddy died. What do you want to do about it?" And then he can sort of choose to escalate, because it might be above his pay grade what to do. He perhaps didn't sort of create the actor or and stuff like that. So then he escalates up the hierarchy, or he might decide to do something about it and restart the actor or take over his work and things like that. And all that can be done, thanks to isolation. That these actors are completely self-contained, autonomous units that doesn't have any strong coupling with anything else.
So basically, the end user could build, let's say, some checkpointing at the actor level, and then if they say, "Oh, this person that I was dependent on, is supposed to give me 10 units of work," and they gave me 5 units of work and then died, I could use my checkpoint to sort of go back to an earlier state where that person hasn't given me any work, and then reboot them and kind of can keep going.
Exactly. And things, everything. So the way normally organize it is just like an organizational hierarchy, that you have like bosses or whatever you want to call it. Like we call it the actor parent. So any actor can be a parent by simply by creating workers, and by escalating sort of when you receive a notification, a message from one of your workers, then you can choose to do something about it or escalate up, and you can also have this sort of sideway error notification, because it might not be you that created the actor, but you might be dependent on him, right, or something like that. So then it's also interesting to get a notification that the worker that you're dependent on, or the actor you're dependent on, it failed. And you need to encode this type of sort of a cursor or indexing in the protocol, of course, so you know where you were or where you when you died. But usually, I mean, if you retain that information, that can be sort of relayed up to the sort of parent, and the parent can then sort of kick off yet another worker, sort of, and resume in him where the other one failed, so to speak, if that makes sense.
Yeah, that makes sense. So how does this work with respect to sort of data flow? Like, let's say you're like the play framework, for example. I guess all of these actors are communicating with the same database. And so that's is that the way that they read and write information?
Yeah, that's a great question. That sort of leads into one of the features we have in Akka. That's sort of persistent of state is nothing that's sort of encoded in the core actor model. Erlang has their way of doing it. They're essentially using a distributed database called Amnesia, where you put information in and out, sort of a key value store, you can say, but it's a little bit more than that. While in we have taken sort of another route where we based our persistence on event logging. So each actor, if you choose it to be persistent, has an event log in which it stores the events that it sort of receives. I don't know if you're familiar with event sourcing and versus command sourcing or so, but
no, I've actually never heard of that. To be honest,
okay.
Yeah, so go for it.
Okay, well, we don't need to go into those semantic details, but essentially, what it does is it simply logs the messages that comes in or the events it creates representing the state change coming out of that, of receiving that message, actually. So it might receive a message. It decides to actors are side effecting. We haven't said that. They're not like purely functional or stuff. The whole point of actors is to do stuff when they receive messages. So they are side effecting. Mm-hmm. And so whenever you receive a message, you have the opportunity to create an event representing the state change that you did for the as an effect of receiving that message. And then we have a way of logging that event representing the state change to a persistent event log that is sort of replicated and fully durable, fully decentralized, and all those things. And then since all events representing state changes are logged in order as they happen. When an actor fails, what we do is simply replay the event log, bringing the actor up to speed where it was. And the beauty of having this event log is that you can use it for a lot of more things than just bringing up the actor when it failed. You can actually having other consumers of this event log, for example, replicas that make sure that they sit and read events constantly, so they're always hot. Or, for audit purposes, you have like strong audit log, everything that went on in the system, you can just go in and see. Or for debugging purposes, you can sort of having a one actor that's essentially sort of only sits and read events and replicates them to an external system that you can use for replaying things when things go wrong. In much slower, like event after event, and sort of debugging the system to find out what went wrong and things like that. So it opens up for a lot of interesting things in having this type of architecture with event logging, I believe.
Yeah, that totally makes sense. So what's the connection between the actor model and the reactive programming? So reactive programming, as I understand it, I've used a little bit of Angular and some React.js and things like that. And basically, in this environment, you have parts of the website are sort of just monitoring for variables to change. So, for example, a very simple example, you have some Angular website, and you say at the top, it's going to say hello name, and maybe at the very beginning, the name is just empty or null or something like that. But then very quickly, the name gets populated. And then as soon as that happens, the hello name is monitoring that variable. And it says, oh, the name has changed to Jason. So let's put hello, Jason. And this all happens so quickly that, and there's probably no rendering along the way that people don't notice that's what's going on. But under the hood, there's a lot of like monitoring and sort of triggering. And so that's sort of how I understand Angular. Like, how does that reactive model kind of compare, or how does that work well with Actor?
Yeah, that's a great question. First, I would have to say that reactive has started to become a sort of quite overloaded word. It means a lot of things. People have one context or one way of mapping that, or it means one thing to, for example, a web developer, another thing to for perhaps a low level systems programmer, etc., etc. And the way I look at it is that it's sort of I see it as two different categories. The way it's sort of the whole family of reactive. I see it as two different things. First, you have reactive programming. And we can I can briefly explain what that means, at least what I think it is. But we also have what we usually call reactive systems, and I think I see them as two different things, and one is for local for programming local things, while the other one is to model distributed systems or distributed communication.
Okay.
And one is a subset of this. So I see reactive programming is a subset of reactive systems. But if we start, I can get back to reactive systems. But if we should start with reactive programming, so reactive programming is really about I see it as sort of a variation or a subset of asynchronous programming. Where the whole idea is that the availability of new information drives the logic. So you have this sort of data flow graph, that's extremely lazy, that doesn't do anything unless the information is available, and then as soon as it's available, it flows downstream, like so triggering a bunch of behaviors of changing data flow of variables and things like that. So it sort of allows you to sort of decompose the problem into multiple sort of discrete steps that are well defined. And each step can be executed in a fully asynchronous and non-blocking fashion, which is great. Like maps very well to modern hardware like multi-core and things like that. And then they can be recomposed to produce a workflow or as I said, a graph. And it usually reacts to sort of completely unbounded flow of information, like a stream of information. So there's really no end to it. It just reacts to its environment, so to speak. And reactive programming, as I said, it's sort of usually meant for the way I see it, at least, is that it's for local. It's to model local computation. It doesn't really have a distribution model, so it's more event driven than sort of message driven. We perhaps don't need to go into all the semantic differences between them, but the way I view it in short is that event driven is like you simply just sort of emit sort of events to whoever is interested. It can be 0, can be 200, can be 1,000,000. It doesn't really matter, and the guy emitting the event really that doesn't know, and it all sort of is emitted in a fully local fashion, while message driven is really about direct communication between parties. So it models sort of direct addressable communication. You know who you're talking to and why, etc. And that means that you can actually use it to cross address boundaries, while reactive programming is really all within one address boundary.
That makes sense.
But sort of the different APIs, if we should talk concrete in a programming model perspective. So the APIs you can sort of categorize into two different groups. I mean, one is sort of callback based. That's sort of this old Node model, or old, it's like older than that, of course, but Node popularized that. We have sort of this event loop with sort of anonymous side affecting callbacks, or the sort of reads event from event sources, but the other one that's sort of becoming more popular now is a more declarative model where you use functions, you use function composition, and things like map and filter and fold and things like group by and these things, and that's sort of the approach that also most of these like distributed streaming products have sort of started to use, and no surprise, I think, because I definitely favor the declarative model because it allows for composition, while the callback model is really hard to compose, and it's really hard to do error handling with callbacks, etc. So the callback hell and all these things. So so we've actually seen a lot of interesting products in sort of the declarative approach to function to reactive programming. One is sort of, none of this is new, by the way, but we've seen it, being popularized. And one is, for example, futures and promises. It's quite an old concept, but it's becoming really, really popular, both in web development as well as systems programming or application development programming. And we have them in Akka, of course. And the other one I already touched upon is sort of streams. And you can run these streams locally, and we have streams in Akka, a project called Akka Streams that implements the reactive streams specification that all runs it locally, and it's a way to orchestrate workflow, and do local data processing in a very low latency, high efficient way. But you can also do it in a distributed fashion, So that sort of sums up my view on reactive programming. I don't know if you want me to touch on reactive systems as well.
Yeah, definitely. That would segue really well into the next part. Yeah. So go ahead.
Yeah. So So reactive system is sort of, as I said, I mean, it is definitely a superset of reactive programming, but sort of try to expand those capabilities into a set of the good design principles, I'd say, for distributed systems. So we try to encode that in what's called a reactive manifesto. It's something I started, and then I later have sort of evolved by through contributions by others. But it's essentially, you know, to try to come up with a common vocabulary and a set of design principles for building modern systems that are ready for multi-core, for cloud computing, and or IoT, you know, data streaming, and all of these things. And I always, you know, feel inclined to say that nothing of this is new. You know, these principles, you know, can be traced back to the 70s and 80s. You know, all the work by Jim Gray, you know, Pat Hell, and some of my old time heroes, and also Joe Armstrong, you know, on Erlang, and you know, the foundation for reactive systems is message passing. It's not being event driven. If you should like talk pure semantics, because as I said, event driven is all about. It really doesn't have a way of doing addressing. You can't cross, you know, address boundaries. While message passing, you know, it's all about sending a message to someone to a destination. So it's really the best way to model distributed communication, I believe. And you know, because I think the key here is that message passing, that what we build on when we talk about reactive systems, is that message passing really create this sort of temporal boundary between components that allows them to be fully decoupled. You know, and they can be decoupled in time, and this is what allows for concurrency. You know, and they can be decoupled in space also, and this is what allows for distribution and mobility and location transparency, as we talked about. This level of indirection and this full isolation that also, you know, it paves the way for self-healing system, as system, recover from failure without affecting other parts of the system. So the Reactive Manifesto sort of ends up with the story of that message passing, you know, can give you resilience through self-healing systems, through this properties of isolation, all these things, as well as elasticity, you know, having the system to grow and shrink on demand, you know, living up to the promise of cloud computing, etc.
So yeah, a number of questions. I mean, so one question before I jump into a whole suite of other questions is, you talk about the sort of orchestration of this sort of dynamical system, right? Is there any work on sort of I wanted to say reactive, but any work of sort of like a really advanced sort of supervision? So, for example, every actor type or every actor implementation, you know, something could monitor those and say, oh, you know, this particular action is very expensive, and I've learned it's expensive because this program has been running for 10 minutes, or it ran yesterday, or something like that. And so we could plan ahead and say, you know, these sets of actions need to run on their own machine because they're super expensive. These other ones are really lightweight. I mean, my guess is there's probably a lot of, I don't know if it's possible in the context of the JVM, but in general, it sounds like there's a lot of open research around sort of supervising and moving around these actors to get, you know, optimal performance.
Absolutely, and we do that to some extent in Akka, and I've always been, you know, long term, you know, the vision that I have. I mean, it's long term. I'd like to see, you know, fully adaptive systems, you know, leveraging AI and all these things, you know. But that's sort of far out. So what we have in practice running, you know, today is simpler, you know, in metrics based routers, for example. That can sort of act both upon, you know, how sort of we more based on low level metrics, you know, latency and throughput and these type of things, and as you say, failure rates and things like that. And we also allow us to sort of tag certain groups of actors as you know, high priority or less priority, or give them different roles and things like that. And that can also be like take into account in how you prioritize work across the cluster. But one thing that we haven't said is that I sort of touched a little bit upon it, but one of the sort of really fascinating things with actors is that even though we implement it in a statically compiled language like Java, for example, or Scala, it's actually implemented in Scala. The actor model by itself, give you a lot of dynamicity, because the actor, when it receives a message, it can sort of redefine its own behavior and sort of prior to receiving the next message. So it can completely change the way it behaves. And this means that it can actually turn itself, for example, if it feels like it is overloaded, it can itself turn itself into a router and spin up, like 20 different routees on other machines even, and start relaying. And once the traffic decreases, it just kills them and sort of restores the old behavior, doing the work himself. So this is perhaps a contrived example, but this is stuff that I don't know if is that contrived, but things are usually more advanced than this, and we have capabilities that sort of solves this better. But it tries to illustrate the dynamicity of the actor model, that these actors are fully dynamic in the way that they redefine what they are, really, and as well as being moved around, along with their state, so that opens for a ton of possibilities.
Yeah, I mean, I think it's fascinating. I mean, I think an actor could try to say, like, is the data, is the I/O going to justify the computation boost I get from spinning up a bunch of sub-actors, and if not, I'll just do it myself or something like that.
Exactly. I mean, it's always a trade-off. There's no right answer. It's all contextual, and even if you have all the information, you probably can easily do the wrong call take the wrong call anyway. So that's why this dynamicity in having sort of where there's no fixed topology. The classic way to distribute it, or at least the way I learned to build the distributed system, was that you have to design the topology of the system up front, where things should run, etc. Right? And then you need to redeploy or reboot things to change. But having this dynamicity means that the topology can evolve and will probably completely change from how you initially deployed it after been running for a while.
Yeah, that makes sense. So what's the difference between, let's say, the actor model and Akka and something like MPI?
Yeah. First, I'd say of course, MPI being native, it can be used for things like probably a lot more low latency. It doesn't have the overhead of the garbage or the unpredictability of the garbage collector, things like that. But also, I personally never used MPI, but does that map to threads directly one-to-one, or does it do multiplexing? Or because that could be one of the differences.
Yeah, I mean, I think MPI is very heavy-handed. So I think every MPI node, definitely needs to be a thread, maybe even a process. I don't know if I think there might be shared memory. So I think each MPI node has to be its own process, if I remember correctly.
Yeah, so I'd say that, there's nothing wrong with that model. That there is a certain case of use, a certain class of use cases that fits that model by having, essentially one worker, sitting, in the same place, so to speak, with all the caches hot. There's no sort of context switching at all. You can just do all the work that you give it with the lowest latency and as possible. That model is great when you have a limited number of workers and a static number of workers, where that you have, for example, 10 workers or 5 workers. So you just want to hand out work and have them go as fast as they can possibly do. The single writer principle is really a really good guiding principle when it comes to modern hardware. You just keep the caches hot, just write as fast as you can, and don't let go, because then you might be suspended. while the actor model, it of course can do that, but a lot more inefficient because it can be sort of rescheduled on another thread on another core, so and it's really hard. There are of course native libraries, J9 libraries, that tries to solve that problem, like pinning threads to cores, and we can pin actors to threads and things like that. But that sort of violates the idea of the model, because the idea of the model is to have hundreds of thousands of these things that give you a very different way of programming, and that fits another class of problems. So it's really comparing apples and oranges. If you're on, for example, if you're on the JVM, there is a great library that sort of implements more of the MPI model. That's called the Disruptor. It was created by a guy called Martin Thompson working for LMAX, building sort of high frequency trading exchanges and stuff like that. Or I'm not sure about the high frequency, but he's been involved in these type of things. But it's actually a stock exchange with, of course, extremely low latency guarantees, and where they have the number of workers fixed, and where the actor model would be a really bad fit. But for a large class of problems, especially when we talk about microservices and these, like in general cloud application development, streaming, all these things, I think Actors is a really good tool to use.
Yeah, that makes sense. I mean, it's hard to know what something is capable of, but it's easier to talk about how it's typically used. And the way MPI is typically used is, as you said, one MPI node per machine usually, and very limited passing of data back and forth. A lot of it is really kind of done by hand, and I think the biggest thing is it sounds like with the actor model, you can kind of build it on one machine and then be kind of confident that it will scale out. Whereas with MPI, it's much more tailored to your specific your hardware and the specific environment. What about something like Spark or Hadoop or something like that? Like one of these, I don't know what you would call like kind of like a big data ETL type library. Like what would be the trade-offs? Why would somebody use, let's say, Spark instead of Akka, or Akka instead of Spark, or something like that?
Yeah, that's a great question, and I think it composed pretty well. First, you can definitely use Akka to build something like that. For example, Flink. I don't know if you know that's built right on top of Akka. You're using all of these features that we talked about, so it's more of a low-level programming model when you only talk about the actor part of Akka. But what we have added is it's a lot of things on top. We have Akka cluster, for example, that's sort of peer-to-peer gossip-based clustering, similar to Dynamo, or Cord, or I don't know what you're familiar with in terms of research papers, but similar to Cassandra, masterless, fully decentralized clustering, and another tool that sort of ties into the streaming, as I said, is the Akka Streams library that gives you a great toolbox to do quite advanced streaming, fanning out, fanning in, doing like data processing and things like that. But we have chosen to only support local processing, focusing more on very, very low latency and high throughput. So if you want to do distributed stream processing, of course you can use something like Akka, but you will have to build a lot of things yourself. You can perhaps stitch together. We've actually have support for that called Streamrest, where you can sort of stitch together Akka Streams nodes, local Akka Streams node across the cluster. And for simple use cases, that's great, and that's why we built it for customers that love that model, but only want to be able to scale out a little bit. But if you have big needs, for doing fast data processing, then you should definitely use the tools like tailored for that, and then Spark Streaming or Flink or something like Google Cloud Data Flow are great models for that. And of course, they compose. You can have actors as being the services to the endpoint, the stateful endpoints. Receiving data, from external systems, or being the application point of as I said, for microservices and stuff at the endpoints of the streaming pipeline, and we so they absolutely compose nicely. Yeah.
That makes sense.
So
one question about the actor model: do the actors? So one thing that I think makes this a little different from something like Ray or one of these other systems is I think the actors can actually send data before they have sort of terminated. So most of the time when you have these kind of systems, at least I kind of think of it as sort of this functional thing where I send inputs to some process and I get back outputs. And so that can fan out however it does. But with the actor model, something could be running maybe even perpetually, and it's sort of like a permanent thing that's getting data, sending data, you're getting messages, sending messages back, but it doesn't have to be just sent back on termination. And I feel like that opens a lot of opportunity.
Yeah, it's really good that you point that out. I should have said it in that one of the sort of the area where actors sort of shine is that is in being long-lived, addressable, stateful objects. In long-lived meaning that they outlive like sort of the context, application context, or scope, stuff like that. And addressable means that you have a stable reference that you can always send message to them. And stateful is probably the most important thing that how it sort of distinguishes from a lot of these other concurrency constructs like most data flows, and I mean they're stateful within, but they terminate and then it's the end of that, or futures that you can have one value, but they're not really stateful in the sense that they are long-lived, addressable, stateful things. So that's really how I should use them. If you only have a need for stateless, essentially stateless data processing, then I would not use actors. There are better tools for that. I will use some sort of stream processing, some sort of data flow graph, or rely on futures or future promises or something like that. Even for local computation, I wouldn't rely on actors. But as soon as you have this exact need that you point out, then actors are extremely handy. So
how does that work when you say they're addressable? Like, is there almost like a DNS type thing going on when you start an akka system where you can say, give me worker 23 or something like that. I want to send them a message, and it will figure out a way to do that.
Yeah, exactly. If you the way it works in akka is that if you just use akka actors, it doesn't give you any DNS capabilities, but it also starts from the top level actor that creates actor, and then you need to make sure that you pass along the references that needs to serve that each actor needs to have, as well as when an actor uses another actor, its reference is actor ref. The handle is passed along. So you can just store away that and communicate back, etc. So that's how you can populate things. But that's of course very limiting, and so one of the features with Akka cluster that adds, the clustering capabilities is what we call sharding. Akka cluster sharding, and that essentially gives you what you ask for. You have this essentially the addresses where actors are sort of gossiped around, and that can change. You can have sort of consistent hashing. Sort of consistently hand out actors. Across the node ring, the set of distributed nodes in the cluster. And when nodes leave and go, that needs to be repartitioned, So and actors would then be reallocated or moved around, and that information, or the new sort of DNS or addressable information will be gossiped around, so everyone has the latest news, so to speak. The address table.
It sounds like the problem of I need a shared, let's just say a key value store. We could treat DNS as a key value store. Like I have this sort of shared key value store that needs to be replicated among all the actors. That sounds like a hard problem. It sounds like there's conflicts that could happen. Someone could just find out about a actor and that actor's already dead or something like that. It almost seems like there's a lot of complexity around having a consistent key value store that's gossiped among all the actors. Like, how does that actually work?
Absolutely, you're right there, and we rely on both like old and recent research there. As I said, this epidemic gossiping is based on sort of not reasonably old papers now, and the same thing as the failure detection algorithms and things like that. But when it comes to replicating of the state, we rely first on vector clocks, which is it's a quite old thing invented by, was it Leslie Lamport back in the day? No, perhaps, yeah, I don't remember. I think so. Yeah, he invented Lamport clocks, and then someone else invented vector clocks on top of that. But anyway, that's quite old. But we also rely on quite recent research when it comes to disseminate sort of state. And that is called something called CRDT, so like conflict-free replicated data types, which is quite recent research. Which actually, vector clock is a CRDT, but CRDT sort of generalizes that by giving you a way of expressing state that sort of in a fully monotonically increasing fashion with a merge function that that it will always merge. So it will always.
It sounds similar. Sounds similar to like this operational transform type stuff, where you can forward port similar. Any of these ideas.
It's very similar. It's sort of, I think it was parallel research. This CRDT was I think started by Mark Shapiro at Microsoft, while this operation transform was a Google, right? So right. I think it was sort of done more or less in parallel. But CRDTs have sort of exploded in the research arena after the initial papers, and there's now models for modeling CRDTs that are not just the simple things like registers and counters, but also things like maps and sets and even to some extent graphs. So you can model quite rich data structure as long as you adhere to the rules, and be sure that they are eventually consistent for sure. They're not strongly consistent, but you can be guaranteed that they will always converge eventually, So you have strong eventual consistency.
That makes sense. Yeah. So just to sort of tie it back to something everyone knows. So if you talk about like Google Docs, so you have a Google Doc, you're editing it, your friend is editing it, and let's say you both go to the same cursor and you both hit delete at exactly the same time to delete some character. Then what's going to happen is one of you is going to arrive first, and that delete is going to take effect. Then the second person shows up with the delete. And basically, to sort of simplify this, there'll be some bookkeeping going on. So we know that when that person hit the delete key, we know sort of their state when they did that. And so the system can sort of modernize that delete or bring it forward in time. And when it does that, it will encounter the previous delete, and it will say, oh, this person didn't really intend to hit delete after that delete. They intended to really do the same thing. And so we'll just not execute that second one. Or we'll figure out some way to amend it. If someone deletes a letter and at exactly the same time another person deletes the entire line, then we'll just delete the whole line. But all of that kind of, it's almost like a git rebase or something like that, but you can't rely on a person to do the merge. You have to come up with a set of rules that can be executed autonomously. Right.
And this sort of like primitive ways of doing that is like last right wins and stuff like that. Is usually not sufficient because you will have data loss. Right. And a lot of key value stores implement it like that, which is quite fascinating. While others, rely on things like vector clocks and even CRDTs to try to actually do proper merge without discarding data.
Cool, that makes sense. So as far as recovering from node failure, is that something that kind of Akka pushes on the user? So I guess Akka provides the user with a notification of a failure, and then the developer has to figure out sort of how to reconcile that.
No, that's not the way it works. I mean, so if the user, if you move, when it's a user, if you then mean a user of one of the actors, as I explained earlier, you have this level of interaction. You have the actor that you talk too, and you never really see or touch or know much about the actor unless you use monitoring software, of course, which you should. but
Right.
from a programming perspective, of course you can subscribe to, as I said, events on how the actor is doing, but you don't have to do that. Since the responsibility of recovering from failure is solely on the runtime, it's on node failure or do. What was the specific question you asked there? I lost it.
No, it's fine. So specific. So if an actor fails, then I guess the system will spin up a copy, but then it also has to notify. Actually, that's an interesting thing. Like if an actor fails, we have to know like who is impacted by that, because it could actually be anybody potentially. So I guess potentially everyone has to be notified of that.
Yeah, everyone that has, essentially the way it works is that, and it can be any number of actor refs, and sort of references to that actor, and if an actor fails, it can be, of course, restarted on the same machine very quickly. But the bigger problem and the more common problem, or perhaps not more common problem, one is user error normally, or running out of memory or something like that. But the more interesting problem is probably on node failure, where the whole machine goes down. And what's happening then is that we rely on Akka cluster there to do failure detection, and that's of course a really hard problem, because there's very easy to have like false positives. Then you might think that the actor or that the node that you're communicating with, we do sort of heart beating, right. Pinging around, and heartbeats might be delayed for various reasons. It might not be that the node failed. It might be that it's just doing garbage collection because we're on the JVM, so it's just really, really slow and it's busy. Or it might just be overloaded with user requests. Or there might be a temporary network glitch so the node is still alive, kicking. And it, that's really hard to do. So we have heuristics, and we have, ways to sort of define certain thresholds for these heuristics. But if based on these heuristics, we have to sort of decide that that node is down. Then we have sort of different algorithms in order to how to resolve that. It can be that we're sort of basing it on. First, I have to say that the problem might, in most cases, is a problem of split brain. That you actually have it's actually only a network disconnect. You don't know, but it might be that it's only a network disconnect, or splitting up the cluster into two different halves. And then you have another problem, that in which sort of side of the data center, should you let keep running, and because if you like just only sort of spin up all actors on both sides, thinking that the other half is down, then you run into the problem that you have duplication, and you can run into all kinds of data consistencies, right? So you need some sort of intelligence here to do a good sort of take a good decision. Like one of the half of the cluster then needs to decide I'm out, and the other half won, or vice versa. And there are different algorithms for that, and we have. We don't need to go into specifics, right? But they're all based on your needs for the use case. One example might be that there is one critical actor that you absolutely need for the system to function to be on one side. And then of course that system wins, even though you only have two actors there, or two nodes there, and 200 on the other one. Sorry. It's really bad luck, or it's like simple majority wins. Where in the majority of nodes will win while the smaller cluster has to reboot or hold. So this is really a hard problem. But once you detected that, it's really about sort of resuming the actors on the healthy nodes, and repartition the cluster to have sort of a balanced sort of allocation of actors on the nodes that are still running, and sort of also sort of gossip around the new address information. So all the actor refs in the cluster, meaning all clients, can start using the actors on the new locations. And from the user of these actors, they should never find out, apart from the latency, of course, it takes for this whole process to happen.
It seems like to sort of program in a defensive way, it seems really important to like segment the data you're receiving from each actor. So like, for example, a degenerate example is where you spin up a bunch of actors and let's say they send messages to you and your job is to just concatenate all of these messages or accumulate all of these messages, right? Maybe they're sending back numbers and you're just adding them up. And so you've added up, you're up to, 1,027, and then an actor dies. Well, now you're kind of in trouble because you don't necessarily know you can't separate the contribution of that actor from the other ones. And so unless that one unless you have some way of restarting that actor at exactly the right spot, then that death needs to sort of cascade upwards because you're inconsistent, right? So it seems like people have to program in a way where they're keeping track of who said what, and that way they don't end up in the situation where they can't recover, right?
Yeah, the way it's usually solved is by using event logging. Then the actor doesn't need himself to keep track of that, but whatever made it to the actor, or more, whatever the actor has actually done, is persisted. So he knows exactly where he was when he died, because he can just replay the log, bring him up to speed, and continue to take on requests. While the sender of those, of course, knows where he was when he sent, because he didn't get an act of the message. And by the way, we have support for that guaranteed delivery as well through replay of resending of messages, deduplication, and at least once delivery as well. So I think we have more or less the whole chain covered if you layer in these things. This is also one of the core philosophies of ACA, is that the bare bones actor don't have any guarantees. It's fire forget, you're on your own, and that's simply because that's the most performant, and that's the least expensive, and some might want that. So why should you pay for more than you absolutely need? But we then have layers that you can sort of layer in terms of reliability. For example, when it comes to communication, you essentially just use a sort of mix in or in a trait called at least once delivery, that does, what it says, at least on once delivery, deduplication, and resending, retransmission of messages, etc. So give that reliability when it comes to the communication. That, of course, costs a lot. Well, not a lot, but it costs, what it costs, of course.
Right.
But you don't need to write it yourself. And when it comes to, on the consumer side, we, as I said, allow you to layer in event logging, which of course also has a cost, because it needs to go down to disk and commit every message. And in order to do that in a strong, consistent fashion, it needs to wait until you have committed the message, down to a reliable medium, which is pluggable, by the way, so you can plug in almost anything you like. But that also has a cost, but you can choose then to layer in the guarantees you need when you need it.
So what about, now there's this, like the whole blockchain thing is getting really popular. There's a lot of like really interesting distributed technologies that are coming out that are distributed sort of, I guess, over the public sphere, I guess is a way to say it. But you have things like WebTorrent and things like that. And in this case, there's many clients can't actually reach each other. Like many physical nodes can't communicate with each other. But you're relying on sort of the whole system to have some sort of graph that is connected, right? And so, can Akka work over something like that? Like, does it have NAT punch through, and is it design? Does the design extensible to that, or is it mostly for sort of clusters where the nodes are able to communicate with each other, pretty reliably and all of that?
first have to say that there are blockchain implementations on Akka, and I haven't used them myself, so I can't talk about the sort of the how the quality of them, but sort of nothing prevents you from. So the actor model by itself, I think, lends itself very well to these type of distributed problem, because it's all just node like stateful nodes and efficient communication between them. But the way we've looked at Akka and the implementation of Akka is that we've always said that it should ideally be used in a trusted environment. Thanks to security problems and things like you can tunnel it, over TLS and things like that, and we have support for these type of security sort of guarantees, but it's not really meant for that type of large super world scale systems. If all you used were like stateless actors, then it would probably work quite well. But where it becomes tricky is with the stateful part, because if you want strong consistency, you can only have one actor in charge, and you need full replication of that state, across everywhere, the whole world,
right.
etc. I mean, it's not really meant for that. Then you need something like blockchain that's sort of meant for being shared in a distributed fashion, in a fully reliable fashion. But marrying the two, having the model of communication from actors and or from Akka and having the state being blockchains. I mean that could absolutely work, but I haven't explored it, but conceptually it would.
Cool, that makes sense. So you founded a company, Lightbend, is that correct?
Yeah, it's a company that when I started Akka about 2009, I had no intention to start a company, but it immediately became extremely popular, and I realized I had to start doing consultancy on it and take support requests. So I started a company in 2009 called Scalable Solutions. And Akka grew out of the Scala community, so I knew a lot of people there. Went to conferences, and I met with Martin Odersky, the creator of Scala, and sort of he and I sort of realized that we should do something together. Akka's built on Scala, and Scala's really getting traction. Akka's getting traction. It could be interesting to form a company together. So we did that, and we launched it in 2011. And we later then, added the Play framework and a bunch of tools around it, and the last year's been working on a fast data platform for distributed streaming, making sense in the streaming jungle, and things like that. So it's been quite a ride.
Cool. And so I guess so 2009, 2011, and I think Scala was really big, I think, at Twitter. Twitter was really pushing Scala. Who are the other sort of really heavy hitters that are using Scala and Play and things like that?
That's a great question. I mean, a lot of the heavy hitters, unfortunately, we can't talk much about.
Got it.
That's always the case. But but a lot of investment banks and most banks on Wall Street are heavily invested in Scala.
I didn't know that.
But also LinkedIn, for example, a lot of the different like social media and also retail. There's a ton of clients. I sort of
Cool.
I don't exactly know who I can mention, without saying. So
that makes sense.
That's why I'm hesitant. I can sort of list along, but then I might say something that I shouldn't say. So
that totally makes sense.
But absolutely, there's a ton of because it is this, even though Scala is of course open source, it is this intersection between what is just a user and what is a client. But Scala's really been taking off immensely. I started using it in 2006, I think. It was quite early, and back then I remember the first conference. It was in 2010. It was like small group meeting at EPFL, and it's been really growing immensely after that. And And
Yeah, I do
it's
some Scala, mostly Spark at my job, and I think it's fantastic. I mean, it's absolutely phenomenal. Sometimes I see some people using operators in a really confusing way, and so I have to like take a moment to say, okay, what is this? What is this operator doing? But overall, the freedom it gives you. I'm a big fan of languages that at least have the option of typing, of type safety. And the Spark framework is absolutely fantastic. And so yeah, I'm a big fan. But I probably
yeah,
started using it um, around 2013, 2014. So I've only been using it for a few years.
yeah. I'm glad to hear that you like it. I think for the use case that you're talking about, I think it's where it really shines because because of the functional side of Scala and the things we talked about for reactive programming initially in this chat. Having sort of first class combinators, like map and filter and fold, and having them easily composed. These are things that's hard with a language like Java that doesn't have first class functions. But I think that's why we see a lot of these companies like Spark and Flink and Kafka. It's also written in Scala.
Oh, I didn't
This is
know
just
that.
lends itself very well. Yeah,
Yeah, I mean, I've done also Java Hadoop, and yeah, it's not pretty. It's like extract data function, but it's actually a class, and it has a function called run or something like that. It
yeah,
becomes very verbose because
it
everything
does.
has
Yeah,
to be a class. With Scala,
yeah.
it feels much more native. I mean, you can add two columns of a data set without having to create a class. I mean, it seems in hindsight, it's very obvious that's the right design pattern.
Exactly. Yeah, yeah, and just have first class closures and things like that makes it so much easier.
Hmm.
And that said, Java added lambdas. So it's a little bit easier in Java now than it used to be,
Oh,
but
okay.
still, lambdas are not functions. In the true sense. So I think they miss out a lot
Yep.
on that.
Yeah, that makes sense. So, what about like the company Lightbend? So it started out with you and the founder or creator of Scala, and have you added a lot of people since then, or is it trying to keep it
Yeah,
pretty
yeah,
focused, or
yeah.
what?
Yeah, we've been sort of growing slowly, I'd say. I mean, we've been around for a few years, like 7 years now, and we've been sort of we're up to 100 around 140 people now, which is
Wow.
yeah, with a sort of pretty sized, well-sized, engineering organization and sales and marketing and stuff like that. So I mean, all it takes, to run a real company. When you start the startup, we was 7 guys, in it. Not in the garage, but at our homes.
Okay.
We started very distributed, and we're still very distributed, which is sort of really challenging. But we sort of try to grow slowly and only grow where we absolutely need. Yeah, when it comes to being remote or distributed, I think we're around 20 countries now, and we're almost at all continents. In like Asia, both Australia and New Zealand. We're in Africa. We're South America, U.S., Europe. We're across the whole globe, which is extreme, super exciting and fun, but it's also very challenging when it comes to communication and meetings and all those things.
Yeah, I mean, not to like go off on a tangent, but this is something that day to day, I've been talking about a lot. Um, dealing with sort of time zone and sort of being able to sort of franchise in a sense the organization, right? And so, how do you deal with the fact that there's people all over the world? They're all waking up, going to sleep at different times. Like, do you use like Slack or something like that? I mean, what how do you sort of keep consistency there when everyone's in different parts of the world?
Yeah, that's a great question. It's everyone. It's still we don't have it all figured out. We sort of learn as you go. But one of the guiding principles that I've had, when building the company from the start, is that there is no such thing like remote employees. It's only distributed teams, and because and the distinction I make here is that it's really really hard to have a team co-located and one or two guys remote, because that means that they talk over coffee and over lunch and things like that, and then they forget to pass that information on.
Yep.
And it becomes very 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 split up and divided, and it's really really hard on the people that are then remote. But if you talk about fully distributed teams, then it means that every single one is remote, and even if they do happen to sit in the same office, they can't communicate. Of course they can talk, but if
Sure.
if there's important information, it has to be communicated over some sort of textual form, or perhaps send a screencast around or something like. But it's mainly text. So having this distinction that for a team, we have had teams that have been fully co-located, and then that's fine. But then everyone needs to be there, else it's a fully distributed team regardless of where people are.
Yep,
And
makes
having
sense.
that mentality sort of helps. But it also makes it hard, when it comes to it makes it tedious, having to write everything down. It takes more time to document everything thoroughly and things like that. But also, it might be harder to do meetings. But one of the sort of also guiding principles that we've had in the past, that we actually had to go away from a little bit now, but that we try to do, is to keep all teams in the same time zone, because that means that they can hang out, on the Slack, and things like that in real time, and don't have to wake up and catch up, on 200 messages and a really hard time figuring out the context. But as I said, we haven't managed to keep that for every team. But for example, the ACA team was fully distributed, but all in one or it might be two time zones.
That makes sense.
So that's something that also helps.
Yeah,
But
I
also,
actually.
when it comes to the tools, it's mainly Slack and email, and Skype Hangouts or Zoom that we use now. So it's just nothing fancy.
Cool, that makes sense. Yeah, I ran into somebody whose company had the exact opposite philosophy. They wanted each team to be distributed, and let's just say it doesn't work. Like, that idea just is not a good idea. I think what you proposed is actually, I agree 100%. I think it's very isolating to have, and it's never going to be balanced. So the odds are not that the odds are high that it's going to be, as you said, one or two people out of 10, across the globe, and the other 8 are on the other side of the globe. So it doesn't really work. But yeah, once you go to the team level,
it's just no fun.
Yeah, exactly. Cool. So if someone is, so we have listeners all over the world. If someone is, just in university, they have a degree in, let's say, computer science or electrical engineering or something like that, and they're interested in, and they're interested in a career at Lightbend. Sort of what opportunities are there? We're actually surprisingly, a number of people have reached out to us and said they literally ended up finding jobs with people we interviewed, which I was pretty shocked. I didn't really expect that, but it turns out this is actually a really good medium for people who are, especially in university, but in general, just engineers. And so what sort of opportunities do you have at Lightbend, and what does that look like?
Yeah, we're very interested in people coming straight out of the university. They haven't been damaged yet. No, just kidding. But it's usually we've been hiring a lot of people right from the university, or very close to coming out of the university at least. And I think that if you're interested in working on hard distributed systems type of things, multi-core, concurrency related things, cloud computing, these type of things, streaming, and all this whole thing with fast data, and also machine learning, and or if those things interest you, you should absolutely apply. And since we are so distributed, if you're the right guy, then we'll hire you wherever you are, more or less, because we have teams that are across all time zones. As I said, all the way, from Japan, far out of Asia, Australia and New Zealand, all the way down to South America, and then the west coast of the U.S. So it's all over the place.
Cool, great. So what's an average day like for you or for an employee? If your day is really atypical and crazy, what's an average day like for someone who works at Lightbend?
Yeah, I think it's different for different people. When it comes to me, me personally, I mainly work with colleagues in the U.S. So for me, I have meetings, all starting from 4 in the afternoon all the way up till 9, 10, 11 sometimes. But that's nice. I can get a lot of sort of silent space, silent time, and time for myself. Thinking, working on stuff without being that interrupted in the day, and then I can be more social and discuss things in the afternoons. One thing also that I have to mention when it comes to the average engineer's sort of schedule is that we have a notion of roles. We do all the support ourselves, and this is sort of one of the things that our customers love, that we don't have a support organization, per se, but it's actually the teams. If you have a problem with Akka, it's someone from the Akka team that helps
Cool.
resolving that. That's sort of quite challenging, taking on that role or that hat, so to speak. But also quite fun. It can be fun to sort of see how people are using your software stuff. And helping them, with the stuff that you built last week. So
That makes sense. Yeah.
So most engineers are juggling these two roles, being sort of developing and doing support, and usually on sort of a few days doing support, and then a couple of weeks hacking, and then back to support and things like that. So
Cool, that makes sense. Yeah, I think it's very hard to build something like this in a vacuum, right? So the best ideas are going to come from those discussions. So.
Exactly. I think without them and without our open source community, I have to say, not just our customers, without the passionate community that we've had, we would never gotten this far. Akka wouldn't even exist, I think, but it wouldn't be where it is even without the open source community. We've been getting so much from that, so many passionate people like talking about it, encouraging things, but also rolling up their sleeves and actually sending in patches and it's really an extremely good example of what can on the good side of humanity, and what can be achieved with people across all cultures and actually collaborate into doing something substantial. I think it's quite heartening to see, actually.
Cool. Yeah, that sounds absolutely amazing. So yeah, Jonas, it was absolutely amazing having you on the show. I learned a lot. This is one of the most educational episodes for me personally.
Thank you very much. I appreciate it.
I think people are absolutely going to love it. Can you give us some sort of what's the best way to reach you or reach Lightbend? So what's sort of like some good communication information there?
Yeah. I think the best way to reach me is probably on Twitter. I'm Jay Boner, JBONER on Twitter. Just reach out, and else Jonas at Lightbend if you want to send me emails. Lightbend.com. If you want to find out, I have my personal website jonasboner.com. But if you want to find out more about Lightbend, just go to lightbend.com or akka.io, akka.io if you want to learn more about Akka. And we have a ton of material both on the Akka website and also on Lightbend, all kinds of this stuff, webinars, recorded webinars and articles and all kinds of stuff. So
cool, very good. And so all of it is totally free to use, right? So basically the business model here is that people can do anything they want with Akka, college projects, even commercial projects, but then you're there to help them if they need some extra functionality or they get stuck or something like that.
Absolutely. It's this open core model where everything, in the core Akka Play, Scala, and supporting tools, are open source, and we try to help the community as much as our customers, but but then we also have commercial tools on top, things like monitoring management, and we have a full, like, as I talked about, the fast data platform is also commercial, but everything that we covered in this podcast, in this call, is fully open source, and yeah, we're here to help. So
cool. Thank you so much again, and yeah, everyone, let us know what you think about the episode. We're feel free to chat on the Discord. If you have any questions, feel free to at both of us, Programming Throwdown at, and Jay Bonaire at on Twitter, or ask on the Discord, and I can pass it along. But thanks again for this interview. It's fantastic.
Yes, thanks, Jonas. That was awesome.
Thanks a lot for having me. I really enjoyed chatting with you guys as well. So it was definitely mutually beneficial.
The intro music is Axo by Binar Pilot. Programming Throwdown is distributed under a Creative Commons Attribution Share-alike 2.0 license. You're free to share, copy, distribute, transmit the work, to remix, adapt the work, but you must provide attribution to Patrick and I, and share alike in kind.